Welcome to Lesson 3.2, Day 2, Solving Systems by Elimination. The objective for this lesson is to solve systems of equations algebraically using the elimination technique. So that elimination technique will have us eliminate one of the variables, hence the term elimination. So we have our system of equations. Okay, we're going to get one of the variables to eliminate. That will result in an equation which is one variable, and we'll solve that equation. And use that solution to get the remaining variable as well. So in essence, we're trying to do the same thing that we did in the substitution technique. We're trying to start with a system of two equations with two variables and whittle it down to one equation with one variable, get our answer, plug that answer back in and get the remaining variable, right? But the process by which we get there is a little bit different. Instead of making a substitution, we're going to add our equations together in hopes that one of the variables will eliminate. Now, in order to set up that elimination, sometimes we might have to do step number 2, which is to do a little multiplication at the beginning to set up that elimination. And you'll see an example of that. You'll know exactly what I'm talking about. So we choose which variable we want to eliminate. We do that multiplication if necessary to set up our elimination. Then we add our equations together. I like to add them together. Some people like to subtract them. But subtraction leaves us open to making more mistakes, in my opinion, so I choose to add. And then once we get that answer, we'll solve for the remaining variable, use that solution to get our final answer as well. So we're going to do two examples today, and here is the first. 2x minus, and I want this to be a 1, so a typo on my notes there, that needs to be a 1y right there. 2x minus 1y equals 11, and 3x minus 2y equals negative 12. All right. Let's suppose we just added these equations together right away. Right? We would get a 5x minus 3y equals negative 1. We did not get any of the variables to eliminate at all. So before we add these equations together, we've got to do that step of multiplying by something in order to set up that elimination. Now, in theory, you can eliminate either the x's or the y's. It doesn't matter. But with this term having a 1 as a coefficient right here, I think it's probably going to be easier to multiply and eliminate the y's, because I'll only have to multiply the top equation by something. Like if I wanted to eliminate the x's, I'd have to multiply the top equation probably by 3 and the bottom equation by negative 2 in order to turn this into a 6x and a negative 6x. But I'm going to eliminate the y's because I think it'll be easier. So I want the coefficient for the y's to be opposites. Right now the bottom one is a negative 2. I can turn the coefficient in this top equation to a positive 2 if I multiply by a negative 2. So I'm going to multiply this top equation by negative 2. Okay, everything in that equation gets multiplied by a negative 2. So I start off with a 2x times negative 2, which is a negative 4x. Then I've got my negative 1y times negative 2, which will give me that positive 2y that I'm looking for. And then finally 11 gets multiplied by negative 2, which will give me a negative 22. The bottom equation does not need to be multiplied by anything, because these x's will already be good to go, right? I got my 3x, then I got a minus 2y, so now my y's have coefficients that are opposites, and that's what I want, because I know then that these will eliminate when I add these equations together. Okay, so let's go ahead and do that. Let's add these equations together. We got negative 4x plus 3x will give us a negative x. These y's will eliminate. That was the whole point of doing that multiplication, right? So they'll cancel out. And then on this side, we will have a negative 22 and a minus 12, which will give us a negative 34, right? And we divide both sides by negative 1 now to solve this equation. And we get a rather large answer for x of 34, right? I mean, it's possible. We get x equals 34 using that elimination technique. Now, if you box that and you call it good and you move on to the next problem, you would not get full credit for this on a quiz or a test, because we still have to solve for that y. So just like in the substitution technique now, we got to take 34 and plug it in for x in order to solve for y. And we have options. We could plug in 34 right here, we could plug it in here, or we could plug it in here. Okay, we could plug it in here, but I already circled that. That's the same exact thing as this one over here. Okay, so we've got options in regards to where we plug it in. It really does not matter where we choose to do that. I am going to plug it into that first equation because I think that's the most simple in order to solve for y. So dropping this equation down here now, we got our 2. We figured out that x is 34, so I make that substitution. Then we have a minus 1y equaling 11. And now I've got to solve this equation for y. So 2 times 34 is 68 minus y equals 11. I can subtract that 68 to move that over, and then again divide both sides by -1 to get my answer for y. So we have x equals 34 and y equals 57. I'm going to write that final answer here in red. You could choose to write your answer this way, or since our variables are x and y, you definitely could write that as an ordered pair if you want to. You know, x would be first, 34, and then y would be second, 57. Either one of these is perfectly acceptable. I usually only write it as an ordered pair when my variables are x and y. Anything else, you know, I just keep it simple and write it as blank equals and blank equals. But here you could write it as an ordered pair. So this was an example of the elimination technique, and just to be frank and honest with you and transparent with you, I would put this one in maybe the medium category. We did have to multiply one equation by a number to set up this elimination. The easier problems will be set up already, where you won't have to multiply at all, and the system will already have one variable where the coefficients are opposites. The more challenging problems are going to have you multiply both equations by something, which I say it's challenging, but really just kind of adds one more step to it. So let's do one of those examples. Let's do an example where we've got to do potentially some extra multiplication. Now I'm looking at this one, and I said that we would have to do some extra multiplication, but I really don't think we have to. I'm thinking we're going to get either the x or the y to eliminate just by using a little bit of multiplication with one equation and not having to do both equations. So, like, let's say we want to eliminate the x's in this situation. I can get these coefficients to be opposites if I multiply this top equation by 2. That way I'll have a 6x, and that works out perfectly with the negative 6x underneath. So multiplying this top equation by 2, we got a 6x, we got a minus 4y, and that equals 10. Again, multiplying everything by 2. This bottom equation doesn't need any multiplication. So I guess I don't have an example of that here today, but you'll get a chance to practice it in your homework, where you've got to multiply both equations by something to set up that elimination. Well, let's add these equations together now, and maybe if you're looking ahead a little bit, you see something that a little bit different is going to happen here. These x's eliminate, but the y's eliminate as well, and over here when we add this together we get 17. So we got both variables to eliminate here, which can happen, and we ended up with this equation that's not true. 0 definitely does not equal 17. Well, thinking to previous chapters when we were solving equations and things like that, when all of our variables eliminate and our equation that we end up with is false, recall that in that situation, there is no solution. There is no solution to this system of equations. There is no ordered pair x comma y that can satisfy both of these equations. If you were to graph both of these lines then, remember that these would be parallel. They would never intersect. There's no solution. And that can happen when you use that elimination technique. Now, let's suppose that both of the variables canceled out and you got something that was true, like you got 0 equals 0. In that case, there would be infinite solutions. That would mean that the two lines, if you were to graph them, are exactly the same. They fall right on top of each other, meaning that there's infinitely many points, x comma y, that would satisfy both equations. So if both of your variables eliminate, if you have an equation that's false, like this one was, the answer is no solution. If you end up with an equation that's true, like 0 equals 0, then there's infinitely many solutions. And we already talked about how that connects to the graph of that system. So this was lesson 3.2, day 2, all about that elimination technique. Remember that there may be some problems where you have to multiply both equations by a constant in order to set up that elimination. We did not have an example here, but we did have a few good examples to work with. So that's it. That's 3.2, day 2. Thank you for watching.